section, we're going to be looking at chemical equilibrium, how it affects salts, buffers, and indicators. So we're going to be looking at the pH of salt solutions. We're going to be looking at how salt solutions are affected or how they can sit at an equilibrium and how this affects the pH. Then we're going to be looking at what buffers are and what indicators are and how to choose an indicator. So quick recap. Bronsted-Lowry again. We've got to remember that our acid is a substance that donates a proton and our base accepts a proton. We need to remember that for every acid, we've got a conjugate base, and that's formed by losing a proton, and that for every base, there's a conjugate acid, and that's formed by gaining a proton. Again, a reminder that water is amphoteric. It can either donate or accept a proton, therefore it can be treated as an acid or a base. If you remember the second slide on the last PowerPoint, you had some examples of water being used as both an acid and a base. Right, reminder of the key equations we needed. So I think look at this one. We've got a pH equals a half pKa minus a half log C. We can use that to work out what the pH is roughly for a weak acid. Watch what you're given in the question. Okay, I'm trying to explain this as I think it wasn't 100% clear in the last one. So if you're given the concentration of the acid, it tells you it's 0.1 mole per litre or something like that. That's the value for there. pKa, it will tell you either a number, or it'll tell you to use the data book, or it will tell you to use the Ka value. If it tells you to use the Ka value to work out pKa, you need to use this equation. Okay, don't just take the pKa value out the data book if it tells you to use the Ka value. Usually you'll be able to just take pKa out the data book, but just read the question carefully. If it gives you the pH can go there, and you can rearrange it to work out either the pKa or what log C would be, and in turn what C would be. If it tells you the hydrogen ion concentration, this is the bit I'm not happy about with the last slide. If it tells you the hydrogen ion concentration, take the negative log 10 of it, okay? And that'll give you the pH, which means from the hydrogen ion concentration, you're working out this value. Your pKa you should be able to get from the data book, or they'll give you it, or they'll tell you to use the Ka to work it out, and then you'll be able to work out concentration of the acid. I hope that clarifies things. Right, we've met salt solutions in National 5, and we know that how they're named, that depends on the acid and the base that's being used to make them. Up to now, we've always assumed that our salts will have a pH of 7 because our salt is produced when the acid and base go through a neutralisation reaction. One of the products we get is water, the other one being the salts. Now, if we were reacting together a strong acid and a strong base, that would be true. Okay, so if I took sodium hydroxide and hydrochloric acid, reacted them together to get sodium chloride and water, I would find that the dissolved salt within the water had a pH of 7. Okay. However, not every salt or every soluble salt has a pH of 7. Why is it important that it's soluble? Let's just think back. If you get a bit of pH paper, a dry bit of pH paper onto any solid, you will not be able to take its pH. Okay, it needs to be dissolved in water. Basically, it needs to be dissolved in water so we can start to detect how many hydrogen hydroxide ions are present. Does that make sense? If I was to dampen my bit of paper and touch it, I then should be able to take the pH as long as it's soluble, the substance I'm testing. Another thing is, I don't know if you remember, but if we ever tested ammonia gas, we had to dampen the pH paper and stick it at the mouth of the boiling tube. Why would we have done that? Possibly in fertilisers, you can heat an ammonium chloride fertiliser up with soda and it'll break down, and you can put a damp bit of pH paper at the mouth of the test tube, and as the ammonia gas passes along the test tube, you should detect an alkali. Okay, if you try it, what you possibly have done with Dry pH paper, nothing happens. It has to be damp pH paper. Right, so if we have a soluble salt where we've got a strong acid and a weak base, what would happen is we would still have some of that base as molecules, okay? Therefore, what we would find, because it's a base, yes, we'd be in equilibrium, but there would be a lot of H positive ions left, okay? So what I'm saying is the acid would fully dissociate. So if I've got if I've got hydrochloric acid, I'd have my H positive ions, my Cl negative ions, and if I was reacting it with ammonium solution, I would have some NH4 and some OH negative ions, but I would also have ammonium solution. So I'd also have NH4OH as a molecule, okay? So yes, as I've said, there will be an equilibrium, but when our hydroxide and hydrogen ions try to pair up, what we would find is there would not be enough hydroxide ions in the initial solution for all the hydrogen ions to combine with to form water. Therefore, we would still have an acidic solution and the pH would be lower than 7. Alternatively, if we do it with a weak acid and a strong base, so if I use ethanoic acid and sodium hydroxide, my sodium hydroxide fully dissociates, but my ethanoic acid doesn't fully dissociate. We still have molecules of ethanoic acid left. This means that there won't be one hydrogen ion for every hydroxide ion. Therefore, we'll have excess hydroxide ions and the pH will be greater than 7. Okay? Yes, the equilibrium will mean that the ethanoic acid continues to break down, but at the point that we take the pH, there will still be molecules of ethanoic acid for the alkaline solution. Okay. Right, some examples of this, and we do need to consider the equilibrium of what's going on. So we're looking at this the other way around. We've made our salt and we're looking at it in water. Okay, so we've got our ammonium chloride and it's going to fully dissociate into water. But our water will only partially dissociate. So what we're saying there is that the ions of the hydroxide will we've got our salt ammonium hydroxide and it's going to fully dissociate into ions. But we've got our water partially dissociating. Now, what we will find is the concentration of the NH4 and OH ions is going to be greater than what it would be normally for ammonium hydroxide. Okay, so to try and counteract that, what will happen is your ammonium hydroxide ions your ammonium and your hydroxide ions are going to form ammonium hydroxide molecules. This is going to remove your hydroxide ions from the water. Therefore, you've got more hydrogen ions. Your chloride ions, they are happy to be dissociated even when associated with hydrogen ions because hydrochloric acid is is a strong acid and it fully dissociates. Okay, so we're looking at the salt here. We're looking at the fact that the salt fully dissociates. We've then got to look at the ions present and we're comparing that to the ions we would have for the weak base that relates to that salt. Okay, what we've got present in terms of the dissociated water and more importantly the ammonium ions, because they're going to be completely separate, is a higher concentration of those ions in comparison to what ammonium hydroxide would usually be. Okay, therefore your ammonium hydroxide molecules are going to form, causing the reduction in the hydroxide ions. Yes, the equilibrium for water is going to shift to counteract that, but while that's going on, there are excess hydrogen ions. If we look at sodium ethanoate, that again is a salt, and that salt comes from sodium hydroxide reacting with ethanoic acid. Okay, our sodium ethanoate will fully dissociate in water. but as we know, water is only partially dissociated. So what then happens is the ethanoate ions, for the exact same reason as the ammonium and the OH and the hydroxide combined, this time it's hydrogen, the ethanoate ions and the hydrogen ions are going to be a higher concentration at that point than they would in the weak acid ethanoic acid. Therefore, our molecules are going to form. So the H positive ions from water plus the ethanoate ions will combine to form molecules of ethanoic acid. Okay? We're removing H positive, therefore we're disrupting the equilibrium of water to try and compensate for that. But there are excess hydroxide ions and therefore we've got a basic solution. We just need to remember that our soaps are salts and they're made from strong bases and weak acids. That means if we were asked a question about a soap, it would be alkaline in solution because it was a weak acid that was reacted with a strong base. Now, the questions on the next page have come from higher. This section used to be in higher as well. And again, it was removed so as the assignment could be put in. They're slightly different from the other questions you've got, but as in that they're multiple choice mainly, but there are a couple of equilibrium ones that you do need to answer. Okay. You have only got the answers on the next page, which you'll see by my quick flick there. So the answers are there because the questions are relatively straightforward and far more straightforward than the previous questions you've done. Next, we're going to look at buffer solutions and why we use them and what they're formed from. Okay, so our buffer solutions are used to keep the pH approximately constant when we add a small amount of an acid or a base or we dilute the solution with water. Our buffers will either be acidic or basic. If it's an acidic buffer, what we're going to have is a weak acid and one of its salts from a strong base. Okay, it's extremely important that we remember that our acidic buffer has got weak acid and a salt from its strong base. This helps with the chemistry of what's actually happening. Okay, so in this example, we're using ethanoic acid and sodium ethanoate. Ethanoic acid being the weak acid and sodium ethanoate being the salt made from sodium hydroxide, which is your strong base, and ethanoic acid. The reason we need the weak acid is to supply hydrogen ions. We need to replace any hydrogen ions that are removed by the addition of a small amount of base. Okay, they're going to be removed because the hydroxide ions are going to react with the hydrogen ions that are present in the solution to form water molecules. This would disrupt the equilibrium, it would disrupt the pH because there's less hydrogen ions. Therefore, we need something to replace these hydrogen ions, which the weak acid does. Okay. If we were adding the acid though, what would happen is we need the conjugate base, we need the salt, that's where the conjugate base comes from, and it must absorb the hydrogen ions from the small amount of acid. Okay, remember our conjugate base is formed when, your conjugate base forms when the acid loses or donates the hydrogen ions. Okay, basic buffers. These work in a similar way, but this time it's a weak base and a salt that's made with a strong acid. So if we stick with our weak base being ammonium hydroxide and our strong acid coming from hydrochloric acid, we'd have ammonium chloride. Okay, what's going to happen is our weak base will remove the hydrogen ions that are added when the acid is added, and at the same time, your salt, your conjugate acid, is going to replace, it's going to dissociate, it's going to break up and replace those hydrogen ions that were removed by the addition of the base. Okay. For a quick recap, we've got to remember that if we add a base to an acidic buffer, the hydrogen ions are going to be removed. If we add an acid, we need to donate more hydrogen acids and they come from the conjugate base or the salt. If we've got a basic buffer and we're going to add an acid, we need something to remove the hydrogen ions that that are added when the acid is added. Therefore, we need the weak base to do that. Meanwhile, if we are adding a base, hydrogen ions are going to be removed, so we need to find something to donate those hydrogen ions. So what would happen is the salt or the conjugate ions is going to dissociate, producing those hydrogen ions to replace the ones that are removed by the base. Okay? So this is just some information about buffers, and it's just telling us why it's important. They are actually more important in terms of biological systems, although we do use them in chemistry as well. Okay? So basically your blood has got a pH of between 7.35 and 7.45. So if an acid goes in, you wouldn't want there to be excess hydrogen ions and it'd be pulled down below 7.35. Therefore, you need a buffer there to replace any ions that are removed by the H positive any hydroxide ions. Add a base to it, it needs to be the opposite. You need to add ions in to replace any hydrogens that are removed by the base. Okay? Right. We do need to be able to calculate the pH of buffer solutions. Okay? And this is done using the acid dissociation constant, which are Ka, and also the log. Sorry, you're going to work out the pH, you're going to need the pKa and the negative log of the concentration of the acid and the salt. They should be given to you in the question, okay? So one thing to note though, if you're doing the calculation and you get a negative pH, swap your salt and acid over. So salt is on the top line. And that'll give you a positive pH. Right, I've done the first example here. What to do when you're doing the calculation though is do the concentration of the acid divided by the concentration of the salt before you take the log. The figure for the concentration of the methanoic acid and from the sodium ethanoate, so for the acid and the salt is in the question, okay? And it tells us that pKa is 3.8. For question 2, we're told that the buffer solution, both the salt and the acid are 0.1 mole per litre and the pKa is 4.8. The next set of questions you will need to, it only gives you the concentrations in the data book, in the question. You will need to use the data book as it says to get the pKa value. First one is worked through, thereafter it's done the same way, but the first one is done for you, the rest are on the answers are on the next sheet and they're worked through in the same way. Again, pKa from the data book. Be careful. When you get to question 7, you'll notice instead of giving you the concentration, it's giving you a mass that would have been dissolved in water to make the solution, okay? So you will need to work out the number of moles and then work out the concentration of the acid. So for the first one, I haven't worked out I haven't shown you how to work out the gram formula mass. I've just written the gram formula mass down to try and get the information onto one sheet, okay? It is the number of moles that I'm going to put into that calculation. Watch when you get to number 9. It is negative, the answer, so you will need to do salt divided by acid rather than acid divided by salt, okay? You may want to leave these ones till August. These ones you're trying to work out the concentration of the acid and the concentration of the salt from the pKa and from the pH. Basically, to do it, you work through the calculation, put in the two figures you've got. Then you're going to have to do the reverse of log 10, so you're going to have to do the inverse log of 10, and you're going to have to make your pH negative, okay? The first one gives you the value for the acid. You then are going to have to swap the figures, the salt and acid concentration values around. So you'd have salt on the top rather than acid to work out the salt. Okay? Please remember when you're changing it that your log 10 is going to be positive for the flipped salt and acid concentration. Basically, the figure you get when you do the calculation is the value for the top line. Although the bottom line is there at that point, we are ignoring it. Okay? That's why I'm saying you might want to leave these for the moment. That is the salt calculation worked out for you for the first one. The acids and the salts for the rest are shown there. Right, the final section is on indicators. Now, indicators are used to identify the end point of the reaction. Okay? It's not necessarily the point at which it's neutralised, it's the point at which the reaction is finished. Now, when we're using our, so I'll go back a stage, it's not necessarily neutralised because we know fine well that depending on what substance we use, our pH of the salt solution may not actually be 7. Okay? So it's important that we select the correct indicator for the reactants that we are using. Okay? Our indicators are weak acids, and they dissociate in the exact same way as other substances. So in this, we have got our weak acid, or HIN. We've got its conjugate base, which is IN negative. We've got our base here, our water acting as a base, because it's amphoteric, and we've got its conjugate acid there. Okay? We can use this to show that we have got an equilibrium constant. So because it's a weak acid, it's going to be a dissociation constant. It's represented by KIN, and we've got H3O positive times IN negative. So that's the two substances from the right-hand side, the concentration of them, divided by the concentration of our original acid. Water's not there. Can you remember why? The other thing we need to know is that the colour of the acid is distinctly, it's very different from that of its conjugate base. Okay, so the colour we start with of the weak acid is what we've got initially. The colour we get at the end point of the reaction is going to be an obviously different colour. Right, now how this colour comes about, or how this colour change comes about, is to do with the ratio of the acid ions to the conjugate base ions. Okay, now the theoretical point at which the colour will change, or the colour of the indicator will change, is at the point where KIN equals the hydronium ion concentration. Okay, so we want our dissociation constant to be the same as the hydronium ion for the point of the indicator to change. In reality, it's very, very difficult for us to actually see this. And what we find is we need them to differ, or the concentration of the weak acid and its conjugate base to differ by a factor of 10. Now, our pH range of what we're going to use is a value of pKIN plus or minus 1. Okay, so by that I mean if your pKn value, your pKIN value is 3.4, you're looking for something with a pH between 2.4 and 4.4. Happy with that? So when we're choosing our indicator, we need to refer to our titration curves. Okay, what we've got here is the first two. The next ones are on the next page. So we've got our strong alkali and our strong acid, our strong base and our strong acid in the first one. We can see that our strong acid initially was down just below pH 2. We were adding the alkali. As we add it, the pH increases very, very slowly till we get to the point at neutral. Okay, that's, if you look, it's a very, very steep point there, and that can just be a drop of alkali that causes that. Okay, so it's causing a change from about 2.5 all the way up to 10.5. Because we're using a strong alkali and a strong acid, the point of neutralization for this one is actually 7. Okay, that's what the X is indicating. And as we can see, as we keep adding it, another drop, or another 2 drops, it'll very, very quickly be up to a pH of 12. Again, for this one, we've got our weak acid If we have a look, pH is closer here, it's up at 7, and we're adding a strong alkali to it. So if we look, we've still got a distinct length here where we can look at the point that the reaction finishes. It's not as long as it was with strong acid and strong base. More importantly, the middle of it, the point at which the reaction is finished, the point at which we have neutralized it, isn't at 7. The pH is, but it's not, by looks of the scale on this, it's not even 9, it's closer to 10. Okay, it should be halfway though between that straightening off and that straightening off. And what we'll find here is that the pH at the point at which it neutralizes, or sorry, the end point, not at which it neutralizes, but the end point is higher than 7. Okay, this one we've got our weak alkali, our weak base being added to a strong acid. Again, the pH starting below 2, suggesting it's a strong acid. And again, we've got this curve here, a decent length, where we can work out halfway down at the end point of the reaction. And the end point of the reaction for this one is going to be around about 5.5. So pH again is not 7 at the end point of the reaction. Okay, again, one more drop of our base and the pH will increase greatly. Now, what we will notice this time is as we're adding it, it's not anywhere near as high as a strong alkali would give, okay? And this is to do with the equilibrium between the weak alkali and the strong acid, and the fact that we've got more hydrogen ions to our hydroxide ions in the ratio. Okay, all it's pointing out below is that the sharp increase is a point where neutralization occurs. The end point is a better way to use. Oh, sorry, I've missed my weak acid and weak base one. If we look here, there's not a very long steep line. Okay, we've got a weak alkali, we've got a weak acid. The middle of the line is pH 7 because we've got the weak and the weak. It started round about 4, finishes round about 10. But the important bit is there is not a big gap here. Because of that, it's actually very difficult, as you will see in a minute, to find an indicator that would be suitable to work with a weak base and a weak acid. Okay. So what we're looking at in our titration card is a rapid colour change. The rapid colour change is what happens at these long straight lines. Okay, so there's one, there's the second one, and the third one. So we're looking for those long straight lines. We don't have a rapid change in this one. We don't have a long straight line. It's the end point that's X, and as I've said, it's not necessarily pH 7, it is about halfway up. And that's why I shouldn't be calling it the neutralization point. It's okay for the weak acid, weak base, and for the strong acid, strong base, but not for the others. We can calculate where the endpoint actually is, as I said, by working out where halfway up is. This is just repeating what I've said or pointing out what I've said about the fact that we look for the rapid change, and that makes it possible to select a suitable indicator for our weak base, strong acid, our weak acid, strong base, and our strong base, strong acid. Okay, but because there's not a rapid vertical line on the weak acid, weak base, we cannot choose a suitable indicator. Right, we do need to think about indicators. Please learn these indicators, learn the name of them, learn where the pH colour change is, and what the colour is of the weak acid and the conjugate base that goes with it. The pH ranges are actually in the data book on page 20, but the colours aren't. Okay, so they could give you a graph that looks like this and ask you to choose a suitable indicator. So you could, as long as you didn't need the colours, you could just use the data book. You could say you're looking for something that would change colour at around pH 6.5. So have a look through page 20 of the data book. Sorry, I don't mean 6.5, I mean 5.5. Have a look in the data book. Well, methyl red is between 4.8 and 6.0. That's probably a bit too tight for this because we're very close to 6. Bromocresol purple is 5.2 to 6.8. Possibly, I'm looking for one if there's a better one. 5.4.6.6 is p-phenyl, nitrophenol. I wouldn't use that. That's too close to 5.5. Litmus, 4.5 to 8.3 is down as its alternative name as well in the data book, azolitmin, but you will know it as litmus paper or litmus indicator. Okay, I myself would opt either for the methyl red or the litmus for those ones, for that one, I should have said. Okay. So as I say, there is a guide, but it doesn't include the colours in the data book. There are no questions set up for this afterwards. That's why I was giving you an example of a question you could come across.